several months and years. This shows the Grand Canyon here and how much we've learned about early life from those rocks. This shows the Gale Mound that we will be able to navigate. So we're talking about a rock record that's probably as extensive and certainly maybe covers more time than in the Grand Canyon. But of course, everybody's sitting here saying, well, you know, isn't there any evidence of intelligent life on Mars? All these things that I've shown you, and yet we still want to know if there's another example of intelligent life out there. Well, I'll show you some tantalizing clues. First of all, we found smiley face. You know, it's a little bigger than the one you see as a emoticon, but there it is. That's one example. Oh, and how about this? Crater shape, an object shaped like a heart. In fact, we've got two examples of that. So, you know, what does that mean? But of course, these are all orbital images, and to really get into the definitive identification of intelligent life, you got to go to the surface. And here we have a replicate observation that maybe we've got some promising evidence coming up here. Anyway, these are showing future missions. We're going to continue with orbiters and landers, ultimately with the idea of bringing a sample back to Mars from the right place, taken to the right laboratories to answer this question of whether we are truly alone in the universe. Thank you very much.
That was outstanding, right on time. So here's what we got, folks. We've got about 7 or 8 minutes. There's a couple microphones out here throughout the auditorium. We like to step up to those microphones. What I'd like to do, if you have children, kids in front of, or behind you, and they're at the microphone, would you let them go? I'd love to hear the kids speak. So after that, if you have a question, feel free to step to the microphone, please.
If you wanted to do a cheap mission to Mars, what are some of the hardest problems that you have to overcome?
Okay, let's see, I'm trying to think of what the 3 hardest things to do to go to Mars. The hardest is landing safely from orbit to the surface. The second hardest is I guess the second most dangerous thing is the launch of, you know, from the Earth. And the third nastiest thing is to be able to insert into a Mars orbit, into a Mars presence. As part of it. So the hardest, the most challenging part is just getting there. Entry, descent, landing is by far the most challenging thing. So an orbiter is just, in terms of risk and cost, is just a much more economical thing. But as you can see, getting to the surface is really the punchline. And so I guess another way to answer your question is you use heritage from entry, descent, and landing systems that you know have worked. And the 2020 rover mission that's now being designed, we're going to use that heritage from the Curiosity rover since it was so spectacularly successful. So, and there's a cost risk too, because to do things right is not cheap, and people want it to work, so that carries a cost. Yeah.
So obviously, despite the lack of an oxygenated atmosphere, and the lack of indigenous life from physical sustenance, early Mars actually seemed like a good place for human sustainability. But over time, what forced it into the giant red rock that we know today?
I'm sorry, that last question, what was that?
So, from early Mars to now, over time, what forced it into the dry red climate?
Okay, great, thanks. Yeah, okay. The really important aspect of that is the fact that Mars was much more volcanically active in the past than it is today. And volcanism plays a very important role in maintaining the atmosphere. So as the volcanic activity declined over time, the CO2 in the atmosphere got weathered into the rocks, and the atmosphere, which was always pretty heavily in CO2, just basically dissipated. Also, some fraction of the atmosphere was lost to space. Mars is a smaller planet, so it can't hold on to gases as well as the Earth can. There's the MAVEN mission, which has now just been inserted around Mars, is going to measure all the processes that cause loss of atmosphere to space, and so that will give us a much better understanding of just how severe this loss problem was. So it's a combination of Mars becoming quieter geologically and not pumping out as much gas, and the fact that being smaller, it's lost atmosphere to space. So those are two very important factors.
From the information that you got from the previous missions, do you have enough evidence to figure out what happened to all the water and the wetness and the temperature drop on Mars?
Okay, yeah, so the water story is one, it's interesting. You know, you have water on the Earth, in the oceans, but you also have water in the crust. And the water penetrates as far down as the crust has cracks that can accommodate it. But at some point, because of temperature and pressure, the rocks anneal together, all the crack space is sealed up, and water can't penetrate any further down. So the heat of the interior of the Earth actually helps to keep a lot of that water near the surface or on the surface on the Earth. And the same thing applies to Mars. Mars is smaller than the Earth, therefore the crust is cooled more dramatically. So whereas you have brittle crust on the Earth that's maybe 10 miles or so thick, on Mars this is like 40 miles thick. And it's gotten a lot, the cracks, the fracture system has gotten much more extensive over time. So we figured that there was an equivalent of 500 meters of water at the surface of Mars back in this early period. So I've been talking to people all morning, barely. But as the crust has cooled and that fracture space has increased, we calculated it's very easy to accommodate that 500 meters. So most of the water has actually gone down into the subsurface. This is one reason why, if you're interested in modern life on Mars, the subsurface environments, which might have water in it, are very fascinating. A few percent was lost to space. Also, again, the Maven mission will tell us the actual, the precise numbers. So again, it's this combination of going this way or that way, just based on this evolution of the planet.
So you said that Mars dried up over time, like in a period of 4 billion years. So do you think that same process will happen to Earth as well?
Yeah, that's an excellent question. If Mars dried out over time, what's the prospects for the Earth? Well, the answer is that ultimately that's probably true, but the Earth has 10 times the mass of Mars, so a lot of these processes that were as extensive as they were on Mars are much less effective on the Earth because the Earth retains its heat and it's still volcanically very active. That's the key point I made to you about the ocean floors being volcanically active. It's still hot enough to keep that water up near the surface. So I don't know, I guess we got about 5 billion years before our sun turns into a red giant. And of course that introduces some other complications. I would guess that that's probably going to be a more severe problem than the other one. The Earth being 10 times bigger is a big, important difference from Mars.
How fast do the rovers travel, and how do they know what kind of samples to collect?
Okay, how fast they travel and how?
How do they know what kind of samples to collect?
Oh, okay, well that's hard. We get to tell them that. But a rover can actually travel pretty fast. I mean, if you just let it drive, it probably could go 300 meters in one day of operation. We're limited by the wake-up time. We only drive them when it's warm because it would take a lot of energy to heat up the gears and everything. So we have a limited amount of time per day, but in that time we could drive over 200 meters. However, we can only see out so far to tell the rover, just drive it. Don't think about where you're going, just drive it. And that's typically with Curiosity rover about maybe 70 meters, 80 meters out. So we could do that in a day. But then after that, we have autonomy in the rover, and we can say, think your way through from there. Well, now you're limited by how fast the computer can think. And that tends to slow it down by about a factor of 5. So in a good day, we might hit 100 meters or so. But as you can see, it's mostly limited by navigating safely rather than how fast that we can turn the wheels. So, yeah.
I was just gonna ask, how expensive is it to make a rover, and how long does it take to make it?
I'm sorry, can you get a little closer to the mic?
How expensive is the rover, and how long does it take to make it?
How expensive is the rover, and how long did it take to make it? Is that right? Okay. The cost. Well, the cost of Curiosity is estimated at about $2.5 billion, and that's spread over how long it took to make it. And you're talking about on the order of about 8 years or so, 8-9 years. So that's $2.5 billion spread over 8 years. And that's the initial conceptualization, the engineering design, which is actually the most expensive part, and then the fabrication, the launch. So there's this general rule, and that is if you make a great discovery that you want to respond to, it's called Maclise's rule. It's about 7 years, between you make a discovery that influences what you want to do to when you can actually launch the spacecraft. So, and that's just due to a lot of infrastructure, just the way the system works at this point. So yeah, these things are not cheap. Now, we're talking about a rover in 2020, and it's going to get a lot of spare parts off this rover, and so that really helps to bring down the cost. So we're learning to become more economical with these spacecraft. And that budget is a big deal. I mean, that's what really limits the rate at which we proceed.
Well, hey, I just want to wrap up and thank everybody for coming out today. I think it was a great experience, a great conversation. One more round of applause for David. Our national talk session. Our next session will be Ask and Answer Expert panel. It will start promptly at 1 o'clock. Thank you very much.